Now continuing with part 2, the model property preservation. We'll ask, how do properties of models depend on the aggregation, disaggregation process? We'll see that exact morphisms are very rare. And we will show that approximate morphisms may be much more common. We'll study these questions in the context of Markov models, both theoretically and empirically. Recall this diagram from the introductory talk. And one of the issues we mentioned is how the behaviors and properties of interest of models depend on the location of the model within the chain of abstraction and aggregation, disaggregation. And we said that computational complexity, understandability, descriptive entropy, preservation, predictability, these kind of properties and qualities could go up or down depending on the type, particular nature of the metric or the property involved. So let's look at preservation or predictability, or we'll call it predictivity of models. The idea is we have a base model and a lump model and a structure behavior preserving morphism from base model to lump model. As we discussed earlier, and partition on the states of the base model leads to a mapping, and the blocks of the partition are mapped into states of the lump model, and then transitions among individuals in the base model are mapped to transitions between the states that represent the blocks they're in the lump model. So that we're assuming this kind of structure-preserving, transition-preserving morphism. And we're going to ask, though, what kind of properties are preserved in the transition from the base model to the lump model. And reversely, predictivity is the question: does a given property of the lump model imply that the same property holds for the base model? And our major concern here, as an example, will be recurrent or cyclic behavior, whether it's preserved or not, versus absorbing or acyclic behavior. This kind of distinction in steady state, long-run behavior is especially of interest in Markov models. And we can ask the question of preservation: is the property proven for the base model hold for the lump model? And conversely, if proven for the lump model, does it actually carry over to the base model? So here's a view of that issue. Consider all base models, and for the moment, let's call the base model a system, and break the set of base models into two parts: systems having the property P, and systems not having that property. And then consider all lump models, and models having P and models not having P is the dichotomy there. And then the question is, under the kind of homomorphism or structure morphism we just talked about, do systems having P map into models having P? Do systems not having P map into models not having P? Or is there a cross mapping so that some systems having P map into models not having P, and some systems not having P map into models having P? And in this case, we would say there's a deception, or that the property is not preserved. For example, a main issue is, if a lump model has P, does the system that it represents have P? Or could it be that that system does not have P? Because if this cross-mapping is possible, then it could be that a model having P is created from a system that did not have P, and so the creation of P, of the property, is deceptive. The model has it, but the system it represents doesn't. So there's a theorem by Linden for automata, or more for universal algebras, that positive properties are preserved from the system to the model, and negative properties are preserved from the model to the system. So a positive property is one expressible in first-order logic without the use of negation. And a negative property is one that requires negation to express it. So, a little history. Conditions for inheritance of stability properties for continuous systems were studied by Norman Fu. And he showed that we can have this situation where there are these cross mappings that don't preserve stability, and provided conditions under which stability would be preserved. And he noted that downward preservation of P implies upward preservation of not P. So if a property that is established for a system holds for a model, then the reverse is that a model not having that property comes from a system not having that property as well. And properties of interest, however, don't seem to be expressible in negative form. Siraki applied Linden's theorem to usual homomorphisms of finite automata, and showed that interesting properties such as reachability, connectedness, reversibility are positive. They can be stated in a positive way, and therefore that they cannot be established from system to model. So, on the other hand, upward inheritance of positive properties holds. So, if a model has a property of reachability, then it does reflect truly that the system has a property as well. However, downward inheritance holds for negative properties. But as we've seen, negative properties or properties of interest typically are not expressible in negative form. Sadawi and Wiener showed that some properties flow upward from safety-timed automata verified in UPAL to real-time advanced devs models. So there's an instance again where proving a property for through model checking for a simplified model can imply that the property holds also for the more complex system from which it's developed. So here our question is, are steady-state behaviors of Markov models preserved upward, downward under lumping? And our approach is examine the underlying directed graph of the Markov matrix, the adjacency matrix. And so what we have is a graph that reflects the transitions, state transitions, and interpret the acyclic directed graph as absorbing for Markov behavior, and a cyclic directed graph as representing the current behavior. Now, first of all, DEVS makes it easy to discuss this in crossing deterministic to stochastic realms. So we have the class of deterministic DEVS, for example, finite deterministic DEVS, and stochastic DEVS, for example, the finite probabilistic DEVS, and Markov models developed from that class. So we can start with deterministic models with no input in first instance, and then the mapping with a partition to create a Markov model can be done, shown here. So we block the states into classes and create states in the lump model. And to get probabilities for the state transitions, we count the number of transitions from a block to another block. So in this case here, there are 2 transitions, and in this case there's 1 transition, so there's a total of 3 transitions out of the this block, and 2 of them go to this block, so we have a probability of 2/3 make this transition, and a probability of 1/3 to make this transition. So we can create Markov models from deterministic models, and that is a simplification or abstraction because we can be greatly reducing the number of states. And then we can go further within Markov models and use the lumping procedure we'll talk about, which is very similar, in which we aggregate states together and compute appropriate probabilities for the lump model. So we'll do an empirical investigation here. We generated 10,000 pairs of randomized stochastic matrices and state transition pairs. So we have square matrices and for each square matrix, we randomly generated a partition for it and created a lump model for that partition. And this provides the details of how this generation was done. So what we found is illustrated in this table. The pairs are categorized according to how many cycles were detected in the base model and how many cycles in the lump model. So the instances in which there were no cycles in the base model and no cycles in the lump model, in which we consider acyclic or absorbing behavior, was 38. Number of instances in which there was no cycles in the base model, but one cycle in the lump model was 147, and one cycle in the base model and 0 cycles in the lump model was 28. And by far the largest number was where both models have one cycle. Now, a cycle here represents a fully strongly connected model. This is the most common case where the models generated were strongly connected, and then under lumping they remained strongly connected. However, there were other cases going up to 4 cycles, 4 strong components, so they were not connected among themselves, but only internally. Otherwise, there'd be only one, and they could map to different numbers. But the ones that we're interested in here are the strongly connected and absorbing cases. So this is another depiction of that result where we have connected acyclic digraph and a strongly connected digraph, and the numbers mapping here with the digraph homomorphism, which we talked about, that is preserving of transitions. And a cycle is known to either map to a single state, if it is an equivalence class itself, or to a proper cycle. This is a theorem that states that if C is a directed cycle from in the lump model, then a homomorphism, there's a homomorphism from the base model to the lump model if and only if the base model contains cycles of length divisible by the length of the lump model cycle. If you have a cycle in the lump model, either it comes from a connected acyclic digraph, or it comes from a strongly connected or cyclic digraph. However, there must be a cycle there which is a multiple of the cycle in the lump model. And that's quite easy to see that this must happen. And that's a theorem proved here in 2003. So we'll talk about preservation and predictivity for Markov lumpings. And we'll see that both of these nearly hold for recurrent steady-state behavior, but not in the absorbing case. Now recall that we're interpreting acyclic structure in the digraph as eventually absorbing behavior for the Markov model, and cyclic structure in the digraph as eventually recurrent behavior for the Markov model. So on the preservation, we can go from base to lumped, and we see that if the base model is recurrent, then there's a very high probability that the lump model is recurrent. So we can state the base model recurrence is inherited, or if it's true for the base model, it would be true for the lump model with high probability. However, can't state that for the absorbing case because there's actually a higher probability that the lump model will be recurrent if the base model is absorbing. Going back to the cycles and acycles, or think of a sequence in which sequence of states which is not closed and therefore is is acyclic, and that leads to absorbing behavior. But that sequence can be become closed into a cycle with the partitioning, because the initial and final states can be mapped into the same state in the lump model, giving the appearance, you might say, deceptive case of possible recurrence, and that happens more than the case where the sequence remains acyclic. So we cannot state that base model is absorbing, that property is inherited. On the other side, the predictivity, again, if we look at the recurrent case for the lump model, with high probability the base model is also recurrent. So we do have the upward case, or predictivity. The lump model predicts the base model with high probability, but not true for the absorbing case. In the absorbing case, we see that the base model can be almost equally probable. If the lump model is absorbing, it could be that the base model was absorbing, or the base model was recurrent. Either case leads to lump model being absorbing with the same probability. So we can't say that the lump model accurately represents the base model if the lump model is absorbing. Could have been that the base model is not absorbing. Let's look at some other kinds of properties. Counting the out degree of transitions, the lumping usually reduces the number of transitions because we're reducing the number of states. But it turns out that the average out degree of the lump model is usually less than the base model. That is, the number of transitions out of a state on average is usually less than the base model. And here we see that the average out degree of the base model is plotted in blue and plotted so that it always increases. And the corresponding lump model out degree is plotted in orange, and it turns out to be mostly beneath the blue curve, so that it's quite clear that the lump model usually has fewer state transitions out of any particular state than the base model. In contrast, the predictive uncertainty is increased by lumping. The trajectory entropy of lumped model is usually larger than that of the base model. Here we see the same kind of plot. The base model trajectory entropy is plotted, increasing, and the lump model counterpart is plotted for each value. And the lump model may have typically more uncertainty or trajectory entropy, so that's usually larger than the base. So it does look like the predictive uncertainty, or the ability to predict what will happen, is actually increased, so that it's less predictable after the lumping than it was before. And that would be certainly true for starting with deterministic models. Back a few slides ago, in the deterministic case, then there's no uncertainty about the trajectories. There's only one transition out of a state, so there's always a predictable trajectory. So in going from deterministic to stochastic, we can see that this would be true. However, it may be a surprise that it just seems to be true largely for the case where we have Markov models and the predictive uncertainty is actually increased with the lump model, except perhaps for large values of the that uncertainty. First of all, trajectory entropy is the entropy of all trajectories from any of the states for a model. So it's really some summary property of how predictable the behavior is. Now let's look at exact lumpability, and we'll take an example from Wikipedia as shown here. Note that we start with stochastic matrices so that the sums along the rows are 1, and that the probability of a transition from state, say 1 to 2 is 3/8 here. So these are all the probabilities from going out of state 1 and must sum to 1. And partition maps states to states into blocks, so that states 1 and 2 in this case are mapped to state 1. States 3 and 4 are mapped to state 2. And then the lumpability is can be regarded as a morphism that sums the relevant transitions out of a state to a block and takes that sum as the probability of transition. And that requires that the sums are the same for states that start from the same block and end in the same block. So we have here an example where the sums all are equal, and similarly for the other blocks. So this mapping, because of that strict equality, can easily be seen to be preserved under single-step transitions, and that is what's called lumpability. And the lump model has the same steady-state behavior as the base model, modulo this partition. So the steady-state behavior of the two are the same in this case. But what about this matrix? It still is stochastic, but does not satisfy exact lumpability. If we introduce an epsilon and add it to some value like a half here, and subtract it from another value in the same row, we maintain the stochastic nature of the sum is 1, but when we do the lumping along the rows restricted to blocks, then we may not have equality anymore, because now the sums here differ by epsilon. And so instead, what we'll do is take the transition probability to be the average of the row sums. So we'll in effect take all the elements, add them up, and divide by the number of rows to get the value. And now this, so we'll get, for example, here 1/8 minus epsilon over 2, and this is close to the original. So the question is, shouldn't its behavior also be close? Now we have a lumpability metric to measure how close a partition is, and the measures obtained this way consider the sums as samples of a random variable, compute the sample mean and standard deviation, and then the map value is the sample mean. And the measure of closeness is what we call a lumped standard here, is that standard deviation. So we take the sums of the rows within the block, and we take their average as the value, and we take their the standard deviation in the sum as a measure of how close the matrix is. Well, we take the average of all the standard deviations for each of the transitions and take that as the metric. Then we also need to measure the error that's involved in doing this lumping, and we use something called the Jensen-Shannon divergence, which is defined in terms of a more standard entropy measure, the Kullback-Leibler. It is called a divergence because it's not a metric, but taking the square root, it gives a distance metric. And we will measure the approximation error as applying this metric, JSDIS, to the steady-state distribution of the lump model and compared to the mapped steady-state distribution of the base model. So here's how that commutative diagram would look. On the one hand, we have the lump model and its steady state, which has to be computed. And on the other hand, we have the base model and its steady state, which has to be computed. And then we map the steady state of the base model into the lump model space using the aggregation that's underlies the lumpability. And the closeness of the result is measured by the GIS dist metric, and that would be the approximation error. Now, we need to obtain a standard for the metric to get a sense of what it means to be close or far. And we can do that by doing experiments with distributions such as looking at the distance between two randomly generated distributions, the distance between a random distribution and a uniform distribution, and distribution between a uniform and a certain distribution. In other words, certain is where there's a single value. That's 1, and the others are 0. Since that's certain, its uncertainty is 0. Its entropy is 0, and the uniform has easily calculated value. So that distance is represented here, and that's the largest expected distance because you're going between uniform, which is the largest you can get, and certain, which is the smallest you can get. And the distance between two random distributions turns out to be, on the average, around 0.3, and the distance between a random and a uniform is around 0.2, and this is as you increase the number of states or the dimension of the state space. So the background error can be taken to be 0.2. This error, this would be the error, and we should expect an error less than this level to claim that it's better than random. So if our lump model has an error that is less than 0.2 in its distribution relative to the base model, then we have a claim to say that it probably is due to the fact of the lumping that it's close enough not to be considered random. And then recalling that the error propagation is self-damping if the gain, recall that discussion where the gain being less than 1 would imply that the error always decreases. And that can be formalized in general as a contraction mapping. And that means that any two states in the base model, or rather in the lump model, take two states, look at their distance, and take a transition for each, and then look at the distance. And the distance should be less after the transition. And so the ratio of after distance to before distance, when maximizing, when we look for the largest such value, that should be less than 1 for contraction mapping. And here we have a plot of this maximum ratio over all the 10,000 pairs that were done, and a histogram of their occurrence. So we see that there's a maximum value of 0.004. So in general, the ratio is less than 1, so there's a contraction mapping. And that's because of the stochastic matrix constraint that the probability distribution is bounded and is mapped to a bounded value, being summed to 1 always. Now let's return to the main question about approximate morphisms. What's the probability of finding a reasonably good approximately lumpable partition by sampling at random? We now have the two metrics available, the approximation error and the measure of lumpability, the lump STD, or a departure from lumpability. So we plot the results of the sampling of 10,000 pairs of matrices and partitions, and on the x-axis we array the pairs by the lumpability index, the departure from lumpability, and the numbers are the reflect the number ordering, the integer ordering, so that at the origin lumpability is exact, and as we increase outward, these are the numbers of successively increasing departure from lumpability up to a total of 10,000. And for each such pair, we measured the approximation error and plot and then smooth to get a better sense of reduce some of the noise. And what we find is that, as expected, the approximation error increases with increasing departure from lumpability and reaches some steady state, let's say background deviation after some value, at some value around the background rate. We can conclude that within approximation error of 0.1 or so, which is half the background rate that which we determined at 0.2, there are about 2,000 pairs out of a total of 10,000. And so the percentage of models that are near exact lumping is about 20%, or fairly high. So let's draw some conclusions and prospects for modeling and simulation methodology support. We've seen that properties of interest may or may not be preserved in the abstraction process. For example, recurrence is preserved from base to lump. If the base model shows recurrent behavior in the long run, then the lump model will also do that. However, in the absorbing case, the lump model may not reflect the base model, and lump model properties may or may not be deceptive. They may not characterize the base model. Again, we've seen that if the lump model is recurrent, it indicates that the base model is, but if it's not, if it's absorbing, then the base model may or may not, almost with equal probability, have been absorbing or recurrent. Similarly, measures of model structure and behavior may or may not behave as expected under aggregation. For example, we've seen the average number of transitions, the average out degree of the lump models does behave as expected, where typically it's less than that of the lump model, of the base model. But trajectory, entropy, the uncertainty in predicting the trajectories in the lump model actually is bigger until the entropy is in a bigger region for small amounts of entropy. The lump model actually has more uncertainty than the base model. Exact morphisms are very rare. They are more like points in a space of searching for good lump models. And traditional Markov lumpability is an example. But approximate morphisms may be much more common, and that supports discoverability by modelers. And the approximate lumpability in the Markov case we illustrated may be, for example, about 20% probable in finding a reasonable partition. So searching the neighborhoods of exact lumpings may be much easier for both human and artificial intelligence modelers. And so much more research should be done, can be done, to understand this aggregation, deaggregation process, and the issues of credibility of models and carryover of properties from base model to lump model, whole issue of model checking, whether it can give credible results is a part of all this discussion. And with that, we conclude this presentation.